function in here. We have summation back, so we have feedback. And this would be your whatever input you have. So that's the error we have here. So we need to add the proportional gain would just be a gain that we would stick in here. Okay. That's all the block diagrams can look like for that. Unity feedback. The unity feedback is there's nothing in this signal, and we only have proportion. What type is the closed loop system? Oh shit. So we need to actually form the closed loop system, right? And then however many. The type is however many zero poles you have. I believe that determines the type of the system, right? So if we just do the math for okay, the transfer function was 1 over s squared plus 2 zeta omega n s plus omega n squared, right?
Numerator is omega n squared.
Omega squared, okay, yeah. That's the typical second order transfer function there. So then what we have is this transfer function here, and we have the error coming out here with proportional gain. So the closed loop transfer function is going to, if you remember what the feedback rules were for the block diagram reduction, you can actually just consider this a single transfer function up top, and that's just going to be kp times omega n squared over s squared plus 2 zeta omega n s plus omega n squared, right? That's essentially what that is. And then I think if I remember right, the feedback was you would have g of s over 1 plus the feedback transfer function times the feed forward transfer function, right? That's if you have, that would be the block diagram reduction rule for that. So then the closed loop transfer function, we just fill it in. So g of s is going to be this up here, kp omega n squared, 1 plus h of s is 1, so kp omega n squared over 1 plus the same transfer function. Wait. That's actually the denominator of that. Squared plus 2 okay, so we reduce this guy and multiply through by the denominator. We're going to get s squared plus 2 zeta omega n s plus, we'll have omega n squared plus kp times omega n squared, so that's going to reduce to kp plus 1 omega n squared, and then in the top we'll have So this is the closed loop transfer function here. Okay, so if you notice, we didn't add any poles or we didn't take any poles away. The denominator is in the same form, so it's going to be the same type. It's going to be type 0 because we don't have any poles at the origin, so this will still remain type 0 for a proportion control. Right? And then with regards to finding finding the final value or the error, we're going to use the final value theorem, which is going to be y steady state,
We can't
which
see
is
it.
in the time domain, is equal to the limit as s approaches 0 of, what's that?
We
Oh,
can't.
sorry. So your final value in the time domain is equal to the limit as s approaches 0 of the bits s times y of s is what it is, right? And you can rewrite that, since y of s is equal to your transfer function g of s times u of s, right? Because g of s is equal to y of s over u of s, so we're just isolating y in that equation. Yeah. So if we have a ramp input, so we have three different inputs. We have step input, we have ramp, and we have what he's calling acceleration, right? So we need to find out what the values for this in the time domain is. Or sorry, in the s domain. So for step input, that's just 1 over s. It's actually well, people use r over s. So r can be like the constant, the magnitude of it. I think he's asking for a unit step input, so this would be 1 over s. A ramp would be 1 over s squared. And acceleration would be, I don't know, I've never really messed with that before. So I'm assuming it's going to be 1 over s cubed. I'm not sure about that. I am sure about the step and the ramp.
Acceleration is 1 over s cubed. Yeah.
S cubed, yeah. So in the time domain, step is, here I know what that looks like. Looks like that. And then the ramp starts at whatever time value, just increases linearly. And then acceleration input, which is not really a common input, with some sort of graph with that. But anyway, this is what you would actually put inside of the limit, because you need those inputs in the s domain. So if we look at this one here, we want to find y steady state is equal to the limit is s approaches 0 of s times this transfer function here times our control input in the s domain, which is going to be 1 over s. So this 1 over s is going to cancel out with that s. And then we just go ahead and evaluate the limit. So this will go to 0. This term will go to 0. So we're just left with what's left in black here. We'll have this. So y steady state is going to be kp times omega n squared over kp plus 1. Actually, omega n squareds will cancel, right? So
KP.
kp over 1 plus kp. That's our steady state value, right? And let's say the steady state value is like 0, right? So we want to stabilize this thing. Or actually, well, typically when you're given a step input, that's what you wanted to track. So if the goal was to track the unit step input, the goal would be for YSS to be equal to 1, right? So if you just look at this, what value of KP would work for this specific controller? What would actually drive y to 0? What value KP?
-1.
No, because then we get a 0 in the denominator.
Overturn.
Infinity, right? So actually, this is a perfect example of how sometimes proportional controllers, because I think when I was running the PD controller, initially I had the derivative set to 0, so it was just the proportional controller. So in that case, with those specific dynamics, a proportional controller was all you needed to get rid of steady state error, but it's not always guaranteed. But an integral controller will always guarantee that. So that's one thing that's kind of good to know. Okay, but all he's asking is for the final value, right? And if he's not giving you a specific value of KP, then this is what your final answer should be, as long as I'm interpreting his problem correctly. So your final answer is going to be in terms of the gains, right?
Okay. So it would just be, and then how would that change the actual block diagram? Because my understanding is after each of them, the block diagram change. It depends, I guess. I don't know.
So no, the block diagram would stay the same. Like this is what it would be.
Right, but when you add a PD controller, won't it change?
Oh yeah. So you would just add. If you're doing this manually, if you're not using the PD block,
Yeah.
you would add. Let's get rid of this. So you would take the error, give it to this guy. We're gonna need another game though. This will be our KD. So you're feeding the error to both of these now. Does it really matter if the gain goes before or after the derivative?
Okay.
Doesn't matter. So now, this whole thing is your controller. So everything that's shaded would be your controller.
Why are we using the PID block instead?
Yeah, but I just kind of want to show,
Okay.
because he was
break it
asking
down.
how would this block diagram change. But yeah, if you're using the PID controller block,
You can just say
yeah, you would just put the
0, 0.
PID block in line with this signal, right, and then tune it appropriately.
Right.
But if we're doing it manually, then we want to add the integral, we just add another branch off of this node that's goes to a KI gain, which goes to an integrator, just gets summed back up into the summation block.
So this is the unity feedback.
Yeah, it's
System.
unity feedback because you're feeding back what your
Right.
actual output is,
Right.
and you're not applying a gain to it. You're applying a gain of 1.
Yeah, and it's asking what is the type of the closed loop system?
Yes, the closed loop transfer function is, I think is what he's getting at, it is dictated by how many poles you have at the origin, right?
Okay.
So if you're able to actually factor out an s in your denominator, so like say you could factor your transfer function denominator s times s plus 1.
Mm-hmm.
So your denominator is actually s squared plus s. That's a type 0, because if you plotted your result zeros as a pole 0 map, you would have a pole at 0.
Okay.
So if you had a transfer function like s squared plus s plus 1, there is no poles at 0, right? So zeros would not satisfy that denominator, right? So that would be a type 0.
Mm-hmm.
And you can have, let's say you factor your denominator s squared times s plus 1, that's a type 2, because you have 2 poles at the origin.
Okay.
So however many poles you have at the origin, that
So
dictates the type of the system.
in this case, with a P controller, with just a P controller, like if you go back.
We would have to do the math to figure out what the closed loop system is. I know for sure an integral controller is going to add an s in the denominator, so that's automatically going to turn into a type 1.
Okay.
I think the same thing probably will happen with a PD controller as well, but we'd have to do the math
Okay.
for the closed loop transfer function and then see how we can factor the denominator. Yeah.
For the type, he showed us a table in class where it was like the unit ramp goes to infinity, the acceleration goes to infinity, jerk goes to infinity, then it's
Mhm.
type 0, and then type 1 you would have the acceleration jerk go into infinity while the unit ramp is just the steady state error. Does that ring any
So
bells?
is he talking about the, because this is what I was referring to, transfer function types. So maybe he's talking about something different.
Yeah, just, this is basically what we got from class talking about types. This being like,
Type 1, your error. Okay, so this is type 1 based on what kind of input you have.
is that what you were talking about when you showed
Yeah,
us
I
that?
think it may be a different interpretation. I've never actually seen that before, or I may not have remembered it before, but what I do know about types is it's basically dictated by the number of poles you have. So it's probably, so he had on there type 0 with a ramp, or sorry, with a unit step input.
Oh, ESS, yeah, the error, and then,
You would get a finite error, essentially what he's saying,
Yeah.
and then the rest are infinity for type 0.
or type 0, okay. So that's probably, it's probably the same thing, because what I remember is just, because I think it's actually in one of the textbooks that I was looking at when I was reviewing all this stuff before I started the semester, but another way to look at it is look at your denominator, see how many poles are at the origin. I'll double check just to make sure, but that also will tell you. But it's probably one and the same. So having a type 0 system means you don't have any poles of 0, but it also means that given a certain set of control inputs, you would get a certain set of errors. So yeah, you use that, let's see if we can find that table online. I'm not really seeing that. Where? Yes, this is kind of what I was talking about here. So we have, you can factor the denominators as 1 for the origin, so you can factor out 1s, type 1. Here you can factor out 2 s's, type 2. Here you can't factor out an s, so therefore it's type 0. So it's probably, it's the same, right? It's just two different ways to look at it. And this is just identifying system type just based on the actual denominator. That's identifying system type based on the input, output, based on the output or the error that you're getting, so. Okay, so now, do you want to finish one with, doing a ramp and acceleration, or do you want to do 2 and 3 using the step?
Can you do 2 and 3?
Using the step input, okay. So, yeah, that's actually probably better. Okay,
How can you switch displays?
for 2, he wants PD control, right?
Yeah.
So, we're gonna have KP,
Okay, can you switch the?
sorry. We'll have KD times the derivative, which in the plus domain is s, right? Just write s there. And then you sum these together. These come from the same node, which is the error. So here's your error. And then this is the controller output, which then goes to your plant. You give S, that's your output Y. This comes back here and there's your U. Okay. So it's the same approach, and we need to figure out what the multiplication of these two are, right? So we have the original transfer function, which was omega n squared over s squared plus 2 zeta omega n s plus omega n squared, and then times this controller here, which is going to be kp plus kd times s, right? So that would be the new closed loop transfer function. We write as kp plus KD times S omega n squared over S squared plus 2 zeta omega n S plus omega n squared. That's the closed loop transfer. Well, not the closed loop, that's the feed forward, the combined feed forward transfer function. So since we have a unity feedback, if we want to find the closed loop, it's going to be this transfer function over 1 plus the feedback, which is 1, and then times the feed forward. And then if we do algebra on that, we're going to get n squared plus 2 zeta omega n S plus omega n squared plus kp omega n squared plus kd s. kd omega n squared times s. And in the numerator, we'll have kd times omega n squared times s plus kp times omega n squared. And then I'm going to rearrange since we have two s's here, two coefficients of s's, I'm going to merge those together. So the closed loop transfer function will have the same numerator. And we'll merge these two together. So s squared plus 2 zeta omega n plus kd omega n squared s. And then omega n squared plus kp. Kp plus 1 omega n squared. So this is the closed loop transfer function here. So this would be your u, that would be your y. And if we want to figure out what the steady state output of this to a step, right? It's going to be the same as before. We have y steady state is equal to the limit as s approaches 0 of s times this guy here. And then times the ramp input in the time domain, which is 1 over s. Those will cancel, this will go away, that will go away, this will go away. So we'll end up with actually the same steady state error as we had before. Okay, I should do that right. It's gonna add s, yeah. So that's just gonna go away, so it's the same. So we actually find in this case that with a PD controller, the value of the steady state error, or you can also look at it as the value of the error because you can just subtract this from the reference value, does not depend on KD. So you can tune the gain for your derivative control all you want, but it's not going to have an effect on steady state error. The derivative controller is strictly just for transient properties, for reducing oscillations and overshoot and stuff like that. Okay? And then, if we have time, if nobody comes in, we can finish the same one, but with a PID controller. So let me...
What was the final result for that?
It was the same as the proportion.
Okay.
Yeah. Because all the terms that got introduced to the closed loop transfer function were just coefficients of s, which went away in the limit.
It canceled out.
Mm-hmm. Well, they didn't really cancel out, they went to 0 because your limit, when you take the limit, you make all coefficients of s 0. So there were no non-constant terms in the numerator and denominator that got introduced from the PID controller. Okay, so now we want to change this, so we're going to add an integral controller. And we're gonna add that there as well. So, what changes here is, we're gonna add a third term, that's gonna be ki times 1 over s. So, ki over s, and then we'll make it n squared. One thing I'm going to do first is I'm going to multiply the top and bottom of this transfer function, which represents this whole transfer function right here. I'm going to multiply it by an s, just to get rid of that ratio in the numerator. So this would be equal to kd s squared plus kps plus ki all times omega n squared, and then now we go up a power in the denominator, s cubed plus 2 zeta omega n s squared plus omega n squared s. So that's the combined feed forward transfer function. And then we apply the block reduction rules to that. We're going to get, copy this to save time. And 1 plus that. So the closed loop transfer function is going to be s cubed plus 2 zeta omega n s squared plus omega n squared s plus kd omega n squared s squared plus kp omega n s plus ki omega n squared over I'm going to go ahead and put the omega n squared in here. S plus ki omega n. And then I'm going to collect the terms in the denominator. So look, we have an s squared here, and then an s, and then an s. Plus omega n squared plus kp omega n squared s plus ki omega n squared. Squared plus kp omega n squared s plus ki omega n. Okay, so now we do the final value theorem on this. Y steady state is equal to the limit as s approaches 0 of s times this whole guy here. And we're doing this with respect to a ramp input, so, sorry, not ramp, but step input, where the transfer function is 1 over s. Those cancel, that cancels, that's canceled, this cancels, that cancels, this cancel goes to 0. And we're just left with ki times omega n squared over ki times omega n squared, which is going to give you 1. So it's tracking, with a PID controller, it's tracking the step input. And this will always happen with an integral controller. When you do the final value theorem, you're just going to be left with the value that you're left with is going to be equal to the value that you're trying to track. So in other words, the steady state error will be 0. And it's the same thing with the other ones, except you're, instead of the 1 over s for step, you have 1 over s squared for ramp, and then you have 1 over s cubed for. We're almost done.
Do
We're
you mind
back.
to ask how long you'll be?
We're gonna wrap it up right now.
All right, yeah, because we got the room reserved. So just whenever you're ready.
All right, any questions?
I missed the first part before the Simulink. Are you uploading that to the Canvas page?
Yeah.
Or- sorry.